Greetings to you who's watching this presentation. I am Maicom Varella, and in this presentation, I'm going to talk about Newton polyhedra and Whitney equisingularity for isolated determinantal singularities, which we abbreviate to IDS. This is a joint work with Luiz Hartmann and Thais Maria Dalbelo from UFSCar. Firstly, I would like to thank the organizing committee for the opportunity to present our work. Matrices, their properties, and objects related to them have applications in many fields. In mathematics, more specifically in commutative algebra, algebraic geometry, and singularity theory, an important class of varieties is defined by the minors of matrices. When such variety satisfies a certain condition on its codimension, it is called determinantal variety. Using Newton polyhedra and Leibniz-Euler characteristic, we present a condition that guarantees the Whitney equisingularity of a family of isolated determinantal singularities. Moreover, given an isolated determinantal singularity X, we use topological and geometric information to establish a Allegro type formula for gems F and G defined on X, which satisfies isolated singularity. This presentation is divided in these topics. Firstly, we define the determinantal singularities. Here we present the notion of strongly equivalence between two matrices and present some important results about it. Secondly, we introduce the concept of Newton polyhedra and present some conditions of general position. Then, we provide a formula for the Euler obstruction of an isolated determinantal singularity in terms of the Newton polyhedra. Also, we present conditions so that a good family of IDS is Whitney equisingular. And lastly, we exhibit a Allegro type formula for gems F and G defined on IDS, given by the Leibniz-Euler characteristic. So let's start our presentation. We denote by n and k the set of complex matrices of size n by k, and n and ks the subset consisting of the matrices with rank less than s. And let A be the map gem defined by AX, with each aijx in the ring OM. And let X be the analytic gem defined by the matrix A. We say that X is a determinantal singularity of type nks in Cm if the dimension of X is equal to this expression. And let X be a determinantal singularity defined by the matrix A, satisfying the condition that or either S is equal to 1 or M satisfies this inequality. We say that X is an isolated determinantal singularity, IDS, if X is smooth at X and the rank of AX equal to S minus 1 for all X different to 0 in a neighborhood of the orange. And in this work, we consider the determinantal singularities of type nkn, and we use this notation. That is, we consider the determinantal singularities given by the maximum minus of A. Two matrices A and M are said to be strongly equivalent if they can be obtained from each other using the elementary operations of these two kinds, between lines and columns. Here we have an important result for the development of this work. Let A and N be two gems of matrices with holomorphic entries and n less or equal k, such that A and M are strongly equivalent. Then N is equal to A. That is, we can realize a series of those elementary operations on the matrix A without changing the set defined by A. We don't know yet if the sets are determinantal. It will depend on their dimension, but we know for sure that they are the same set. Next, we introduce the Newton polyhedra. We denote by xa this monomial, where A is a point on Zn. The Newton polyhedron delta f of a gem of a polynomial function given by this formula is the convex hull of this union, where Rm plus is the positive resultant of Rm. And the coefficient Ca is said to be a leading coefficient of the power series F if A is contained in a bounded face of the Newton polyhedron delta F. Now, we are interested in defining the Newton polyhedron of a given matrix. To do so, we first present some definitions. So let A be a gem of a matrix with holomorphic entries and n less or equal k, we say that B is a basis for a gem A if B is linearly independent and each Aij can be written as linear combination of elements of B, where each Fs is a function on Cn. And if B is a basis for the gem A, then there is a gem M strongly equivalent to A, such that each Mij can be written as this linear combination, where Bijs is different to 0 for all S. In this case, we say that the gem M is strongly equivalent to A with respect to B. That is, each entry of the matrix M is a linear combination containing all the elements of the basis B. And the Newton polyhedron of all the Mij's on the previous remark are equal to the Newton polyhedron of this function. Now, let B be a basis for a gem A of a matrix with holomorphic entries and n less or equal k. The Newton polyhedron of this function is called the Newton polyhedron of the matrix A, and it is well defined by the previous remark. Now, we give an example of two matrices which are strongly equivalent with respect to a base that is formed by the functions x, y, z, and w. As we can see, the Newton polyhedron of both matrix A and M are equal to the Newton polyhedron of the function x plus y plus z plus w. And I could not put all the computations here, but they define the same set, which in this case is a determinantal singularity. It's important to point out that the next definitions and results are mostly based on Sterov's ideas, which may be found on the paper listed on the reference. He presented formulas for the multiplicity and the Euler characteristic of the immunofiber of determinantal singularities in terms of the Newton polyhedron, when it satisfies certain conditions of general position. These results were very important to the results that we achieved, and with the strong equivalence of matrices defined above, we were able to simplify his formulas a little bit. So let A be a gem of a matrix with holomorphic entries and n less or equal k. The leading coefficients of A are said to be in general position if for every collection L of positive weights in every subset I, the set of all points x on C minus 0 M, such that this matrix is degenerate has the maximal possible codimension, k minus the length of I plus 1, where Aijl is the lowest order non-zero L quasi-homogeneous component of Aij. And we say that the leading coefficients of A are in good general position if there is a gem M strongly equivalent to A with respect to a basis B, such that the leading coefficients of M are in general position. And the leading coefficients of A are said to be in strong general position if for every collection L of positive weights, the polynomial matrix Aijl defines a non-singular determinantal set on C minus 0 M. In this case, the leading coefficients of a gem of a one-form double are said to be in general position with respect to A if for every collection L of positive weights, the restriction of double L to the determinantal singularity defined by this matrix has no zeros. And if a gem A is in strong general position, then all gems which are strongly equivalent to A are also in strong general position. The next result is based on Sterov multiplicity theorem, and it was one of his results that we could simplify using the strong equivalence of matrices. And denote the Newton polyhedron of the holomorphic matrix A with n less or equal k by delta, and suppose that delta tilde is bounded, and the leading coefficients of A are in good general position. Then A defines the gem of a determinantal singularity, whose multiplicity is given by this formula, where L denotes the standard n-dimensional simplex, and delta tilde is equal to this difference Rm plus minus the Newton polyhedron delta. In this section, we are going to talk about the Euler obstruction. The Euler obstruction was defined by Macpherson as one of the main tools of his proof to the Deligne and Grothendieck's conjecture. An equivalent definition was given by Bracely and Schwarz in the context of index of vector fields. Lee and Tessier gave a formula for the Euler obstruction of a variety as an alternating sum of its polar varieties, and Bracely, Lee, and Seard proved the next result. So let X be an equidimensional complex analytic singularity GEM with a Whitney certification V, and let L be a generic complex linear form in an open set U containing 0 in Cn. Then the Euler obstruction of X at 0 is given by this formula. Now let A be an IDS. Since A has isolated singularity, there is a Whitney specification of A consisting of two strata, the origin and the regular part of A. And since the Euler characteristic of the Newton fiber at the origin is equal to 0, and the Euler obstruction of the regular part of A is equal to 1, then by the previous theorem, we have that the Euler obstruction of an IDS is given by this formula. That is, the Euler obstruction of an IDS is equal to the Euler characteristic of the Newton fiber of a generic linear form restricted to A. Now, in order to compute the Euler obstruction of an IDS, we present a formula for the Euler characteristic of the Newton fiber in terms of the Newton polyhedra. This formula is based on Sterov Euler characteristic of the Newton fiber's theorem, which we were able to simplify using strong equivalence of matrices as well. So let delta be the Newton polyhedron of an holomorphic matrix A with n less or equal k, and suppose that delta tilde is bounded and n satisfies this inequality. If the leading coefficients of A are in strong general position, then the determinantal singularity A is smooth outside the origin. And if the Newton polyhedron delta F of a gem F intersects all coordinated axes, that is, delta F tilde is also bounded, and the leading coefficients of the F are in general position with respect to A, then the Euler characteristic of a Newton fiber of F with respect to A is equal to this formula. Then, if we replace the gem F by a generic linear form L, we get the next result, which computes the Euler obstruction of an IDS A in terms of the Newton polyhedron of the matrix A. Now, we are interested in showing conditions so that a family of IDSs is Whitney equisingular. Firstly, Gaffney proved that a family of d-dimensional ices is Whitney equisingular if and only if each polar multiplicity from M0 to MD is constant on the family. The polar multiplicities from M0 to MD minus 1 are defined for any variety, and the top polar multiplicity was initially defined only by ices. Nuno Ballesteros and Tomasella defined the top polar multiplicity M1 for space curves as the Müller number of a generic linear projection, and proved that a family of space curves is Whitney equisingular if and only if M1 is constant. Furthermore, for the top polar multiplicity of IDS, we have the work of Pereira and Ruas for codimension 2, and the work of Nuno Ballesteros, Oref Okamoto, and Tomasella. Lastly, Nuno Ballesteros, Oref Okamoto, and Tomasella showed that a good family of IDS is Whitney equisingular if and only if all polar multiplicities are constant on the family. And that's the main result we use on our theorem. So to start, we recall the definition of determinantal deformation. So let A be defined by the matrix A. We consider a map gem such that AX at 0 is equal to AX for all X on Cn. Then we denote by X this inverse image. And if we fix a small enough representative A, then we set ATX equal AX at the point T, and use this notation. If AT is a determinantal deformation of A0 as above, we say that AT is origin preserving if 0 is a singular point of AT for all t in D. Then we say that AT is a one-parameter family of IDS. AT is a good family if in a small neighborhood of the orange, the singular set of AT is equal to the set containing only the orange for all t in D. And AT is Whitney equisingular if it's good and A minus t satisfies the Whitney conditions. Now, we take a small representative A, where A is defined on a small open ball centered at the orange CM. And for each matrix B, we denote the map AB and use this notation. And the vanishing order characteristic of the IDS is defined by this form. Here we have our theorem, the main result of this section. We'll let A be a d-dimensional determinantal singularity defined by the germ of a matrix which holomorph entries A n less or equal k. And suppose that the Newton polyhedron delta of the matrix A is such that delta tilde is bounded and n satisfies this inequality. And let AT be a family of determinantal deformations of A, with A0 equal to A. If the Newton polyhedron of AT is delta, and the leading coefficients of AT are in strong general position for all t in C, then the family AT is Whitney equisingular. Well, the proof is basically the next steps. Firstly, we note that since delta tilde is bounded and satisfies that inequality, and the leading coefficients of AT are in strong general position, then AT is smooth outside the orange. That is, an IDS satisfying this condition has only the singularity at the orange, and this family is a good family. Thus, we are in a contractible neighborhood of the orange, which has Euler characteristic 1. Therefore, the vanishing Euler characteristic is constant on this family, as proved by Nuno Ballesteiros, Horace Okamoto, and Tomasella. Moreover, the top polar multiplicity is also constant on this family, because it is a sum of vanishing Euler characteristics, as we can see on this equality, given also by Nuno Ballesteiros, Horace Okamoto, and Tomasella. The polar multiplicities from M0 to MD minus 2 are computed using the sector equality, which was given by Gaffney, Grullier Jr., and Ruas. Since the left part of the equality is the top polar multiplicity of this intersection, we note that AT has dimension D, and H1 to HL are generic hyperplanes. Then this intersection has dimension D minus L. Then the left part of this equation is the top polar multiplicity, which we already know is constant on this family. For the polar multiplicity MD minus 1, we use these last two formulas. The first one given by Nuno Ballesteiros, Horace Okamoto, and Tomasella, and the last one given by Lee and Tessier. We have that the Euler obstruction of A is also constant on the family, because it's related to the vanishing Euler characteristic by this third formula, which we already know is constant on this family. And all the polar multiplicity but MD minus 1 are also constant on the family. Then by the last equality, the polar multiplicity MD minus 1 must be constant as well. Now, we have that all polar multiplicities are constant. Then, since this family is good, it is Whitney equisingular. Now, we are going to consider a function f, which is isolated singularity, and study the vanishing Euler characteristic of the fiber. We'll let A be an IDS defined by the matrix A, and let f be an holomorphic function germ, such that f restricted to A has isolated singularity. Given a point B in the matrix B, we consider the function fb restricted to B defined by this formula. And the vanishing Euler characteristic of the fiber is defined by this formula. And let A be a determinantal singularity defined by the matrix A, and F a function with isolated stratified singularity at the origin. We use this notation for the intersection between A and the inversing image of 0 by the function f. And let V be a good stratification of A relative to F, we say that G is prepolar with respect to V at the origin if the origin is a stratified singularity of G. And now we have our last theorem. Let A be a d-dimensional isolated determinant of singularity defined by the matrix A with n less or equal k, f a function with isolated stratified singularity at the origin, v a good stratification of A with respect to f, g a prepolar function with respect to V at 0, and delta g the Newton polyhedron of AG. Suppose that delta G tilde is bounded and the leading coefficients of AG are in good general position. Then we have this formula for the vanishing Euler characteristic of the fiber of A and AG. The key point to prove this theorem is observe that AG is not always a determinantal singularity. However, since delta G tilde is bounded and the leading coefficients of AG are in good general position, then by the multiplicity theorem that we presented earlier, AG is a determinantal singularity. Thus, we can relate the vanishing Euler characteristic of the fiber, both A and AG, with the Brasselet number. And the difference between Brasselet numbers gives the number of Morse points in a stratified modification of f in a small neighborhood of 0, and that is our theorem. That's the main reference we use. The second one is the Sterov's paper that I mentioned before. And that's all. Thank you for your attention.